Hi everyone, and welcome to the part 1 of this new series on physics-informed neural networks or PINNs. In this series, we're going to explore how deep learning can work hand in hand with physics to solve real-world problems. In today's video, we're going to start by introducing what PINNs are and why they're gaining so much attention. We'll also look at why they're different from traditional neural networks and from classical numerical solvers. Think of a traditional neural network like a really eager student who memorizes every example you give it. You show it data and it spots patterns. It tries to draw a curve through those points. The inputs go in and the outputs come out. That works beautifully when the examples are clean and plentiful. But the moment your data gets messy or scarce, the student starts to guess wildly, sometimes even breaking the rules of your system you're studying. For a physics-informed neural networks, or PINs, are more of a student who already know the rules of the game. So instead of just memorizing examples, you also hand them the laws of physics governing the equations, the differential equations. So even when they don't have much data to rely on, they're guided by the underlying principles of the system. You can see how regular neural networks behave when it tries to fit the solution. It struggles to capture the true pattern. As you can see, there are bumps, fluctuations, and noticeable errors where the data is thin. Now you can look at the physics-informed neural network. The predictions are smooth, stable, and line up beautifully with the real physics. Even in places where we don't have much data, it still respects the underlying equation and gives a solution that actually makes sense in the real world. A classical neural network only learns from the input and output pairs you feed it. So it looks at the data and tries to figure out the mapping from x to y and minimizes an error, like the mean square error, between its predictions and the true values. This works fine if you have a huge amount of clean data, but the network doesn't actually know anything about the underlying physics. So as soon as you go outside the regions it's seen in its training, its predictions can quickly become unreliable or even completely unphysical. Physics-informed neural network goes a step further. Instead of only telling the network to fit your data, you also tell its predictions that it must satisfy the governing equations of the system. This is done by building a combined loss function made up of three parts, usually the data loss, a physical loss that measures how well the PD residual goes to zero, and a boundary condition of initial loss. We will go into detail on how to calculate all this later in the series. So this forces the model to obey the laws of physics even when there's little to no data, producing predictions that are smoother, more reliable, and physically consistent. Physics-informed neural networks combine deep learning with the governing equations of physics, such as differential equations. They also allow us to model systems where data is scarce, but the laws are already known, improving accuracy and efficiency. So in this series, we will be focusing on solving differential equations using neural networks. So that was a big overview of physics-informed neural networks. So in the next video, we will actually build a neural network from scratch in Python, step by step. Think of it as bringing the theory to life. Thank you.